Okay, so let's start. Um, Hopefully you saw my email about some sample projects from the previous offering. So take a look at them. Obviously you can't do the same topics, but it will give you a sense of what students did, how they organized the project and all. And there's always considerable variance in quality, so you would see for yourself as you kind of go through them that some of the projects were almost like put together in the last couple of weeks, and the others had sort of effort worthy of a good grade behind them. So in any case, take a look at them. What I wanted to do was to go through some project ideas, and I'm going to add to them also, but these are and I think there are 17 or 18 of them. So it's a start, and again, you don't have to do these, but and you can do variants of these or something totally different, and it's all fine. So let me go through it. So the first two or three projects are really Nokia, the telephone, the company which used to make cool telephones, still does, I guess. They gave to a bunch of research groups these things that they call as eSense earable. But basically, earable are devices which go into the ear. Apple's AirPods are an example of that. And one of the trends in these devices is that they're obviously kind of they make sound, so you can hear music and other stuff. Folks. They have they also pick up your sound, sometimes through skull conduction, sometimes through some fancy acoustics and all. But the trend nowadays is also to put a lot of sensors in there. And this particular device, I guess the main sensor it really has is an inertial sensing unit, so accelerometer and gyros. So basically, they're detecting various kind of movement. There are devices with more sensing capabilities. There's a German company called Bragi Dash, which sells something which is like $300 or so, and they say they have 23 sensors. Okay, this is still a technology which is in relatively early stages. Just if nothing else, the battery life is pretty bad. I mean, if you use these things, last for a small number of hours. And also there are other kind of form factors which companies are playing with. So I mean, obviously we're used to the wristband stuff. Google had tried the eyeglass form factor and then kind of sort of failed, I guess, at least in the consumer sector, but there are other companies which are trying it. There's some Japanese companies who sell eyeglasses. Amazon has come out with a ring. There are again a few other companies which make these. And common to all of them is they're partly user interaction devices, so you can speak to them, like in case of Apple's earpods, you can basically interact with Siri in that case. Amazon also has come out with these things. Anyway, the nice thing about this one is, firstly, they were free. They gave like my group 20 pairs for free, so that's nice. But that apart, it's kind of, there's a community around it. A lot of research groups are working on it. Okay, so the project idea out here is that using its capabilities, basically the fact that it has motion sensing and also sound sensing as well, because anytime there's a microphone, you can send acoustics, as well as acoustic feedback capability. You can do a variety of sort of interesting projects. So some of the ideas are by my student Vikrant, and so this one is to basically do a pedestrian alert system. There was a talk earlier this year by a visitor out here from Colombia, and he was talking about this whole notion that if you are sort of crossing the road and all, and if you are anything like me and others I see, you're kind of distracted with your phone and stuff like that. So wouldn't it be nice if there was a car coming in your direction, kind of your device can alert you even though you're immersed in your device. Since it it hears the audio, so to say, so recognize the approaching car and the direction. So the idea behind the direction is that since you have two of these, so you can do some sort of angle calculation and thereby kind of get some sense of that, and use the IMU to say something about the real, like, am I walking in that direction or not, or something like that. So whether it's am I in potential danger, and then alert. So that could be acoustic. So this is an example where you could think of other types of things one may imagine. Another one is head pose estimation, where since you have the IMU, could you track sort of how the head is moving, and then anything around that you could do. So for example, you could imagine that if there was a group of people and all of them had these variables, perhaps you can do group conversation dynamics, who was speaking to who. So you can have a smart transcript, if you may, those kind of things you can imagine, or other applications out there. So another possibility is, so I have kind of a catch-all version of this project where so you can imagine combining what the inertial sensor in your variables is telling together with, let's say, there is a variable, or what that is doing. So like, for example, with the variables, people have done things like detecting drinking, smoking, these kind of things. Perhaps those things can become more accurate if you also combine it with the head gesture, right? Like what's happening to the head. Perhaps when someone smokes or drinks and all, the signature in the variable would be different, but perhaps not any one of these things alone would work great. By combining them, perhaps you can do a better job, so showing whether fusing this data becomes useful. So that's another kind of possibility. Another one is to detect in this whole realm of variables, what if you had variables, could you better detect computer usage kind of activities. So for lots of work, there is interest in sort of monitoring one's work, if you may. So I'm sure you have heard about like how cops have cameras and all, right? I mean, so these are things which are kind of very obvious, but what if you are trying to track productivity of more of like people whose work involves usage of computers, and also by looking at the signatures, could you detect when they were using the computer, what kind of applications were they running, were they interacting with their phones, for example, these kind of things. So could we monitor activity? So there is a whole area in I guess broadly computer science, which is called as human activity recognition. And kind of the idea is that using sensors could be essentially generate a log of the activities that one is engaged in. And early work actually kind of a lot of it happened here at UCLA, kind of focused on the obvious kind of things. Am I walking? Am I sitting, running? These kind of gross physical motion type activities. And in recent times, things have moved to more subtle kind of things. So this computer activity is an example of it, or even things like am I drinking, am I eating, could I detect these things without having specialized sensors kind of all over the body. Smoking, there's a lot of interest in tracking eating habits, particularly people who are I guess trying to wean off too much eating and stuff like that, or wean off smoking. Another area which has emerged lately is, I'm sure some of you may have heard about how there is a huge opioid crisis in this country. So being able to detect when someone is injecting themselves or is even getting into a post-injection sort of stage where their body basically goes into seizure, and again there are unique signatures. So all sort of applications you can imagine, and the active so this whole human activity recognition has taken kind of a bigger role. Sports analytics is another one, or when people are under rehab, like as they are or like bad posture, things like that. So people are trying out all sort of ideas out here, and these projects are just representative of examples in that space. If you're interested in this topic, what I would recommend is that there is a conference called UBComp, UBICOMP, and there is a sister conference which takes place at the same time called International Symposium on Wearable Computing. So you just glance through its proceedings and you'll see all sort of cool stuff that sort of people are doing, and that's a source of inspiration. So project 4 I've just listed as a catch-all around it. So other type of inferences you can imagine, or doing something more foundational, if you may, which is looking at how, as I mentioned, hearable combined with wearable, combined with smartphone, could they lead to an improvement in accuracy? Can you design models, machine learning models, which are tolerant of the changing set of sensors? So what I mean by that is, imagine, again, let's say I've created some piece of software which is continually monitoring my activity and spitting things out. It's generating a log of activity events. But I don't, people normally don't always have exactly the same set of devices all the time, right? I mean, sometimes I take my watch off to charge, and right now my phone is sitting on this podium. So again, it's obviously not capturing any inertial signature, but it's still capturing sound type stuff. Could you design something where, as sensors either disappear because they are being charged or just left on the table or something like that, or just generally are not on or near one to meaningfully capture a signature, could the model be tolerant in the sense that you don't have to retrain the whole thing from scratch or not have an exponential number of models for all different possibilities? So that's another direction to take. Making use of audio feedback. So human activity recognition is basically about taking sensor data and kind of making complex inferences from it. But since these devices have feedback also, so acoustic in case of hearables, in case of wearables, there is the haptic feedback. It can kind of tap on your wrist, if you may. So with these kind of things, you could imagine doing things where there's a feedback component. So a lot of work now has begun to shift towards applications which are not simply sensing, but they are intervening. And the idea is that that intervention could be used to nudge your behavior, okay, in a more desired direction to keep you healthy, for example, or like imagine something whenever I slouch, maybe it kind of just nudges me, okay, sit properly or have a correct posture. There was a cool paper at the recent UBComp, this conference that I mentioned, where this group out of Cornell, what it showed was that when someone was, so the thesis that they had was that when you are stressed and when your heart rate goes up, then having some sort of a sensory input which is lower than your heart rate has a calming effect, and something which is faster than the heart rate aggregates it. That was kind of their intuitive hypothesis, and what the project did was to validate that. And the way they did it was that basically, let's say in a stressful exam situation, sensor detect you getting stressed and all. In their case, it was a haptic feedback. So kind of the tapping on the wrist was related to the stress level and modulated by the heart rate, and they would kind of basically try to calm you down. So that's an example of an intervention that is happening. Other kind of stuff, many years ago in this course itself, group of one team had explored kind of the idea that the type of songs are driven by your mood, okay, or location or things like that. And again, last year in the list that I circulated, another group kind of looked at something similar, which is activity driven song, where the song selection, the tempo of the song and all was basically, of the music, was based upon the activity type. So there are all these kind of ideas floating around as well. So this is I guess P1 through 4 are basically kind of a collection, and I'm really throwing these things out as ideas. I have sufficient number of these hearable units to like have many teams pursue projects in this space. You would need to bring your own phones. I have a few phones, but not sufficient number. It works with both Android and iOS. There is a Japanese group which has created a library for iOS, so it can work with both. When it comes to the wearable component, we do have some wearables. So if you want to kind of explore some combination combination of these things. I'm also open to the idea that if using some other sort of wearable device, which is cheap enough for me to purchase, you want to explore something also. So like the ring form factor type stuff, which has appeared. I think the glasses are still a little bit too expensive, but rings and all are affordable enough for me to provide you with. Any questions thus far? Okay. On the P1 slide, I have a link to the eSense hardware itself, and they have a paper in a IEEE magazine which kind of describes the hardware in more detail. Their web page has a lot of stuff to play with. Okay, super resolution IMU sensing. Okay, so what's going on out here? So it turns out that, so my group does a lot of work in the space of like using IMU sensors to do various kind of inferences and all. And it turns out that in many activities, a challenge that you run into is that the resolution at which you are sampling these the rate at which you are sampling these sensors is too low to capture the dynamics. So just to so typically you will find that the wearables and smartphones and all, they're probably going to be sampling accelerometer and gyros and all at let's say 15, 20, 30 hertz, something in that range. And that's certainly enough for things like walking, running, and all. These motions are kind of at a slower time scale, if you may. But a lot of things that we are trying to do are much faster time scale. So, for example, I had mentioned the computer computer activity detection one. So the student Vikrant, one of the things he was trying to do was that by monitoring the motion of, by monitoring that acceleration signature, can we infer what were you typing, or something about your typing, like what rates you were, at what rate, word per minute and all, how many words did you type. So maybe even if I cannot predict entirely the text fully, but maybe I can infer a lot about it. You could also imagine that from the way you are typing, we can infer things about your emotional state and personality. Like, for example, when we are angry and all, we kind of type in a different style than when we are casual. Or depending upon what app you are interacting with, if you are engaged in email writing or code writing or just kind of browsing on the web, very different signatures are going to be there. So there's a whole bunch of stuff you can imagine inferring. There are also things like people who are better educated, smarter, the ratio of longer words to short words is very different than people who are less educated. Okay, so just the mix of the average length of the word is indicative of something about the person. So now the problem in that keyboard thing is that when we type, sort of the rate at which we often type turns out to be a lot shorter than when we are sampling. So you would be lucky to even have one sample of a keyboard press, let alone multiple, to have some reliability in a case where someone is typing a text. So now what you're faced with is you would basically a couple of things. So one is you can be smarter. So just because the sampling rate is low doesn't mean everything is lost, because you can bring to bear knowledge of English language and all to fill in the things, right? I mean, something similar to what these predictive keyboards and all do. But the other one, the more engineering solution, would be to have a faster sampling of the sensors. The problem though is then it burns energy. So there are devices where which are capable of, the sensors themselves are capable of being sampled at a much higher rate, a few kilohertz even. The problem though is that it's too much data, and also sort of you begin to burn a lot of power. Now, in photography, in recent times, this whole notion of super resolution has emerged. And kind of the idea is that I take a low resolution image, and then using some means, I convert it into a higher resolution image without taking additional photos. And if those of you have done signal processing, the sound smacks of a little bit like interpolation. Except that the problem is interpolation, where you kind of say, okay, I'm going to increase the resolution by a factor of 2, so I'm going to take the nearby pixels and then do something about it. The thing is, it only works when sort of the signal is well behaved and all. So this super resolution, the more newer techniques have begun to take advantage of neural networks, which kind of do it. They give a higher quality result, and they're smarter about areas where there's a sudden change and all, because they can bring to bear a global knowledge of the image also, as opposed to interpolation, which just looks at the local knowledge. So the idea out here is really, could we apply super resolution techniques to IMU sensing? So the project here concept is very simple. You take given a low frequency, low sample rate trace of these sensors, could you generate a high sampling rate thing, which is better than simple kind of interpolation type of things that you might do. And what you would need to do is to first, obviously, to get the ground truth, sample at a high rate, discard the samples, and then see whether you can go back to the high sample rate reliably using neural networks, in particular using neural networks which are optimized for time series. So some of you may have heard of, if you have done any neural network course, recurrent neural networks. So they specifically refer to this. Other related version of this project you could imagine doing, instead of super resolution, missing data. So one other challenge is sometimes there are gaps in the data, and can I fill them? So it's called imputation problem. It happens sometimes because the sensor became faulty, or there was a drop of network packet or something like that. So super resolution and the related one, imputation, and again looking at these newer techniques which have emerged in image processing and computer vision based around neural nets, kind of applying them out here. So that's the project idea. So you can say P5 and P5 prime. P5 prime is the imputation part. Okay, something is missing. One other kind of side note out here. So inertial measurement units. If you look at IMU sensors on kind of websites which sell electronics, you would see reference to things like it's a 3 degree of freedom sensor, or a 6 degree of freedom sensor, or a 9 degree of freedom sensor. So usually when they say 9 degree of freedom, what they mean is it has an accelerometer for 3 axes, so it's measuring linear acceleration. It has a gyroscope which measures angular velocity around the 3 axes, and then it has a magnetometer, which or magnet sensor, which is basically sensing kind of the orientation relative to the Earth's magnetic field. So Earth's magnetic field imposes kind of a sense of direction, and then by measuring against that, you can basically kind of measure the orientation. So 9 degree of freedom, or 9 readings, are clearly excessive if you think about it, right? Because to characterize fully rigid body in space, how many numbers do you need? 6, right? You need the location of the centroid, and you need around that coordinate frame, you need kind of an orientation around that, right? So 3 plus 3, 6. So if a IMU sensor is giving me 9, what gives? So could you identify the redundancy that exists in that sensor? Like clearly I have 9 numbers, but I only need 6, right? So there is excessive information. So what is going on?
Does it have to do anything with the accuracy? Because like the mag reading is not accurate.
Sure, you can. So yeah, it has to do with accuracy. So we are putting XSF 1 to get a cleaner data. But let's imagine, for sake of argument, all my sensor readings were perfectly accurate. Okay, where is the redundancy there? Is there, so between these 3 sensors, accelerometer, gyro, and magnetometer, can you calculate one of them using the others? Right? I mean, that's basically what we're looking for. So acceleration integrated gives you velocity, right? So intuitively, I should be able to get gyros out of accelerometer. Well, there is still a subtle matter of orientation, and also it turns out you can essentially throw away the gyro if you didn't care about noise and all. The problem is accelerometer is extremely noisy, and so if you were to simply do integration, then you end up having a lot of drift and all. Okay, so gyros, since gyros are often used for very precise things, like if you make, like you've seen these apps which use the phone to control drones and all by orienting and all. If you were to simply use the accelerometer to create a virtual gyro, it would be pretty bad. Okay. Okay, so so going back to it, it is because of the noise reason, but in principle it is redundant. Okay, it's okay. So anyway, wanted to throw that bit out also. So IMU, so super resolution and imputation, these are two topics one can pursue if you're interested in it. Talk to Vikrant or talk to me for all these projects. You can obviously talk to me. Okay, this one is an unusual project because it's actually given by one of your peers out here. Swapnil out here, back in Bangladesh, he was engaged in some project. So there's this whole community out there which exists, which is called CubeSat. Okay, they basically are into the business of making small satellites and sort of putting them out in space. And there's a lot of encouragement from national space agencies and all around it. So there are groups all over which kind of engage in this thing. So what he's proposing is that in this particular case, sort of design. So this is a little bit like a hobbyist community, if you may. So you're not talking about NASA or SpaceX and that kind of stuff. This is really resource constrained tiny satellites. How big are they? How big are these small satellites?
10 centimeters.
Okay, 10 centimeter by 10 centimeters, really tiny. Okay, so anything that you do with these things has to be commensurately simple. And so the idea out here is to basically design a protocol stack for these things, so that and a secure one at that. Okay, so again, since the size is limited, obviously power is limited. These things are out in space. You can't even recharge them easily, other than whatever you scavenge from the sun. So you can think of it as a very lightweight, secure communication protocol optimized for these baby satellites. Okay, what so the next couple of projects are by my student Joseph Noor, and what he is working on, and I guess there's some activity in my group where what we're basically looking at is that when you design IoT applications, how are they spread across the device, the network, and the data centers. So I mentioned kind of when I was introducing these things that how modern IoT systems are really kind of these multi-tier kind of things and all. Now, and when I talked about edge computing and all, I kind of referred to that there's a lot of impetus towards kind of pushing computation which takes place in the data center closer to the edge, perhaps even to the devices. Okay, if one could do that. Now, thus far, so what has also begun to happen is that the applications themselves have begun to move towards simply collect the data, make some inference on them, and log them, or change some policy, or develop new science. There, the latency requirements are pretty low, right? I mean, whether a medical researcher gets the data a second later, or an hour later, or millisecond later doesn't really kind of matter to the first order. So I'm sort of ignoring a lot of stuff out there. But imagine now you are a company which is handling a fleet of drones or autonomous vehicles, and you have the cloud component engaged. Now latency suddenly becomes an issue. Now, pushing computation to the edge, all the way to the edge, is fine if all you needed to do was local decision making. But the moment you need to combine results from multiple things, then suddenly you have to have the computation somewhere up here. Somehow that interaction needs to happen. So you could imagine if a fleet of drone is being coordinated, or a bunch of cars near an intersection, they need to be orchestrated. A lot of these things would require at least some sort of interaction among them, or perhaps with some network component. The problem right now is that when it comes to pushing computation out into the internet, our main thing would be to push it onto some server like on Amazon and all. The problem there is the latencies are pretty long. So there are papers which show like what is the latency from an edge device to a typical data center from Amazon, and you would see that kind of the mean latencies are pretty decent. Let's say 100 milliseconds, something like that. If you do things carefully, right, like not situate your logic far away. So just to go from here to East Coast, speed of light is around 20 milliseconds. So if you're going to do a round trip thing, like there you have 40 milliseconds. But fortunately, Amazon has data centers kind of all over the planet. So there is one in Northern California, there's one in Oregon. So there are new closer data centers. But still, the problem is firstly, the mean may still be decent, but the tail is very long. So studies have shown that the tail can get into thousands of thousands of milliseconds, and kind of with some tiny probability. Also, your ability to synchronize across these networks becomes tricky also. So what has begun to happen is that one version of edge computing that has begun is that there are companies, and I've kind of listed one called StackPath, there are some others, one called Fastly. What they have begun to do is they have begun to make data centers much closer to the edge. Basically, what they do is they team up with Verizon, AT&T, these kind of things, and they put sort of some servers right close to the edge of the network, so that now instead of renting computing in Amazon's AWS or Microsoft Azure, you kind of rent computing there. You can basically, they have kind of different models. So like you can put a Docker container in these places, and now suddenly you have a low latency kind of version. Okay, the idea but the space is just very early stages. Okay, I mean there are so what this project is really about is to explore, and it's more of a characterization project to begin with, to understand what kind of latencies and all we are actually seeing from this. So like for example, StackPath says that they have like 45 to 50 such edge edge data centers, for lack of a better word. So the idea out here would be that as things are moving and all, imagine if this is a vehicle and all, or even as you're moving from city to city and all, okay, and if you're doing applications which involve kind of which are latency constrained, could the software adapt to this thing? Okay, so possibility could be that you have code pre-provisioned and running in several places, and then as you're moving, you kind of your state kind of migrates within the code for a state. So very simple version of it. For example, I saw a little demo with in Professor Tabuada's lab, and what they have is they have a drone which is flying in his tiny lab, so it's kind of an artificial construct, but still makes a point. And the local control of the drone is on the drone. So this is the one which is kind of given all the parameters, just tries to maintain the speeds of the motor and the positions of the speeds of the rotors and all. But then the thing which is doing the path planning and stuff like that, somewhat more compute intensive stuff, that is happening in a nearby server. And in this case, as the drone flies, it has a radio, so its connection, it has to change its connection from server to server to server, and then they migrate this code along with it. So you can imagine this is kind of a planetary scale version of it, where latency constrained application, things which may involve some sort of actuation or control, and kind of other kind of things, where you basically are going to migrate the computation and characterize how well, what are the latencies, how well are you able to synchronize stuff. Like for example, if I have two robots which are interacting through such a service at the edge, and they have to do something together, okay, how well you could characterize them, okay, how well you can synchronize them. So we have kind of listed starting from kind of profiling to kind of some sort of an adaptation strategy to kind of something which actually does intelligent placement of this thing. This is there are some projects where we have listed this thing that these are growable projects, in the sense if you're interested in pursuing this project or perhaps something even more, there is headroom to grow. So some of the projects I'm throwing out are kind of ideas which are worth exploring. So they're really kind of early stage in some senses. So that's kind of the notion out here. You would, this is obviously a more software heavy project, less embedded software and more, if you may, non-embedded or whatever, Raspberry Pi and server type software as opposed to kind of those tiny ones. Let's see, am I missing some other point out here? Yeah, okay, so I think, I think I've given, there are I mean, we have given a version of this with stack path, but there are other ideas that we have around it. So if this general space interests you, again, talk to Joseph and me, and we can describe some of the variants. Yeah.
So the goal is to keep the latency low.
And keep the latency under control. So let's imagine your control loop. So controllers, control loops, or any decision-making loops, if the latency is too high, they basically begin to fail to converge and all. So you need to keep the latency controlled as things are moving, and so you have to keep moving the computation.
You're supposed to have like multiple stations. Like
you will have multiple stations and all, yeah. And that's not that unheard of. Like even right now, just for not these type of applications, but applications where a different kind of latency is under issue. I click on a link, how rapidly the page loads. Okay, you may be thinking that I'm clicking on whatever my favorite website.com and that is going to their server and coming down. That's not what happens. There is a company called Akamai and there are a few others. They're called content distribution networks. And what they do is they cache the static content again in servers which are co-located with the ISPs and all. So that's another form of latency which is an issue. The thing is that's a simpler task because it's a static content that you are pre-positioning. Here, there's active computation happening, so you have to position computation, not simply content. But that's kind of the idea. So yes, maintain latency under acceptable bounds. Okay. I guess the other thing is that relative to human type latencies, in these cases the latency requirements are often much tighter, so we are also pushing the limit in that regard also.
I have a high level question, not about one of these specific ones, so maybe you can answer at the end. So there seems to be a lot of variability in terms of if it's more focused on the embedded devices or related to embedded devices, like what you said here about it's going to be more high-level programming. Can you describe kind of what you're looking for at a high level from these projects? Or
Either is fine.
Okay.
So, I mean, remember the course is not about embedded devices. It's about all components of a system which commensurate. So, project focusing entirely on a cloud-located component in service of embedded devices is perfectly fine. So, hopefully that answers the question. Okay, and I mean here I think the baseline one is really characterizing and all. Okay, so I can see a project which is really about a very rigorous systematic characterization itself would be a useful one, and not actually doing the adaptation algorithms and all. So depending upon sort of one's interest and all. There. Okay, this one is so I don't know how many of you have Amazon or whatever, Alexa or one of these kind of things, but the way these systems work is we kind of say something, and then behind the scene, after doing the initial speech recognition and all, they actually figure out which application to get. So if you read up on the way Alexa works is, so when we say Alexa play Mozart on Spotify. I'm not sure whether that combination exists or not, something like that. But the idea is there is a verb, there is a target, and there is an application we are doing. So behind that, it basically goes around figuring out which application to run and kind of what to pass to that application, right? So it does a speech to text conversion, figures out which application you are doing, and then goes through it. So that's what's happening. Here, kind of the idea is that we want to do same kind of functionality, but now take it to the next level, where to do your command, it actually needs to harness stuff running on multiple devices. Okay, so now, so I'm sure you have perhaps seen movies and all about like humans interacting with the smart spaces and all. So now imagine a space where you have multiple devices, so and applications are distributed among them. And what we want to explore out here is that could we give commands and all that require to create a pipeline or some sort of a configuration of multiple such applications across devices to perform a task. So speech recognition technologies are pretty robust at this point, a lot of open source stuff, and also the focus here really is after that initial parsing, could I go out and stitch together things which are happening at multiple places. And we could start out with So he uses this term called macro program, but think of the macro program as kind of instead of a program which was for a single node, it's a program which is stitching together a bunch of building blocks. So the baseline one is that I have a static set of programs distributed over a static set of devices, and by listening to the user command, you are kind of just identifying which one, and that is they can talk with each other. So we actually use a software package called Node-RED to actually make things assemble. So essentially, you kind of are going to say, take this output, feed into this, kind of assemble that pipeline. And then one can go over the set of devices as dynamic. Like for example, I don't know upfront what are the devices and what their capabilities are, so I have to discover them, because this could be that devices come and go as they do in a home, and then finally kind of truly dynamically assemble them. There is a nice NLP component to this thing, because you want these commands to be kind of fluid. You don't want a very rigorous, very rigid kind of syntax that the user has to speak in. So there will be an NLP component out there. NLP stands for natural language processing. There are very robust toolkits out there, so you don't need to become an NLP expert, but you will need to use some of those tools. This actually is very, there is an area right now called program synthesis. Essentially, it is this notion that user states something, and from that you generate a program to accomplish that task. Okay, so this is kind of in that space, except specifically focused around this IoT. So obviously for the simple case, command mapped to a single program, and we just pass the input. That is what indeed Alexa does. Siri, or rather Apple, has kind of a little bit more elaborate something called shortcuts and all, which Google Assistant also has now. So that's kind of the general sense out here. So this one kind of idea would be that some sort of a device to which you can speak to, and then take the sound out of it, and then really focus on the back-end piece out here. So distributed IoT assistant.
Could you give an example? Someone's did a project in this area?
Oh, has someone done a project in this area?
Any project that you
Not this whole front-end part. So what we do have is kind of the back-end stuff, where how you can have things running on different devices could be wired up together. So that is this project DigiFlow, which actually Joseph has been doing for as part of his PhD. This whole voice-based interaction to that, I don't know, to the best of my knowledge, there isn't anything out there. Okay, the thing that exists is, like I said, like single device kind of stuff, single application type of stuff. The example I gave earlier, play Mozart on Spotify, right? I mean, play is a verb which is being input, Spotify is the application. So Amazon has some logic to kind of say, what was the program? So it will say, okay, on. Okay, so what's the object? So there's some front-end parsing which happens. It says, okay, Spotify is likely the program. Is there some application called Spotify in their store? It kind of fetches that. And then applications expose verbs with certain arguments. So Spotify presumably exports something called play, and it takes an argument. Okay, and so that's the interaction which takes place. In a distributed setting, I don't know of anything really out there. Okay. By the way, also sort of, we are not going to simply just hand it to you and leave you in a lurch. Okay, I mean, it's kind of, the idea is that then you speak with the mentor. By the way, I've only listed the names. You can go to, you can just Google them on the UCLA directory. They're all grad students, and sort of locate them. So anyway, emails you can discover, or just go down my lab, which is 1762, just first floor, kind of on this side. Okay. Anyway, so that's this. This one is in the same vein, but it looks at a different facet out here. So if I'm the goal of this project really is that if I'm doing so if you think of the computation pipeline that happens in these things, so you have sensory data coming in, it goes through, you immediately extract some low-level features and all, but after that nowadays typically there is some sort of a neural computation which performs some inferencing, and then another neural computation to do some sort of figure out what kind of action I'm doing, and then finally the command goes out to the actuation, to the actuator. The notion out here is that we want to see how to partition this specific form of computation, neural computation, between the edge and the cloud. Okay, and the notion being that if I'm in a poorly connected thing, then perhaps the computation should be done locally. If I have good connectivity, maybe I can rely on the cloud and have a higher quality computation. So there's going to be a trade-off between the quality of the result, how much bandwidth I'm using, and what kind of latencies I have and all. The goal out here is to be able to do this partitioning in an adaptive manner. So you could imagine one version of this thing could be very static. I'll tell you that you are going to be in this network situation, these are the latencies, and I'll figure out the optimal partition, and presumably you can solve it using a whole bunch of graph partitioning type work and all that kind of exist. What is cool out here is to be able to do it in a dynamic setting, okay, because conditions change, right? I mean, I walk into my home, suddenly I have a higher quality Wi-Fi link available and all, right? So you want this partitioning to adapt to what the state of the network is, which means a component of this thing has to be something which probes the network also, right? Having said this thing, there's a fair bit of body of work that does exist, but they're mostly on the static side. That is, given a characteristic, given a network topology and given the characteristics of it, come up with a partition and like sort of apply some optimization methods to it. So there are various ways you could kind of do it. So there is a dynamic part, and the other thing is there is a heterogeneity part. So what I mean by that is, imagine you are an application developer, and now your job is to figure out what should I run on the user's device and what should I run on the cloud. And your application is going to get deployed on a range of devices. Some people may have that $50 Android phone, and some people may have whatever, a $2,000 Samsung phone. Very different capabilities, obviously. One has 5G and a super duper fancy processor, and the other is probably still struggling with LTE and has a slow processor. So the correct partitioning is going to differ a lot. So now one way you could approach this thing is you'll say, you know, I'm going to design my application, and somewhere there's going to be a table which lists every device that exists and every network configuration, and I'm going to make a massive lookup table and just work with that. But perhaps maybe you could make it more dynamic. That is, the system starts out with a best guess and very rapidly kind of figures out what's going on, what's the speed and all, and then adapts to it. So, so lots of uses out here. So goal would be something which can adapt seamlessly to the end device capability as well as the changing network characteristic. To do this thing, instead of like working with real networks and all, which could be quite a pain, so there is a network emulator that we use, something called Mininet. So Mininet is it's not a simulator. It's not as if you are simulating a network in MATLAB and everything is fake. What Mininet does is it plays some magic with the way networking stack works in Linux, and it essentially gives you a whole bunch of Docker containers or virtual machines which talk to each other on a network where you can control the delay and all. And everything now happens in kind of real time, in effect. Just literally it kind of creates a bunch of virtual machines which are now talking over a fake network which is faking the topology and the latency and the bandwidth characteristics and all. So it basically lets you do experimentations just on the comfort of a decent machine, kind of without kind of worrying about, you know, how do I test it against a delay to an Amazon cloud data center and stuff like that. You can do a lot of stuff very easily, or at least the first cut algorithmic works and all could just be done out there. So we have using Mininet, the student Sandeep. He has Sandeep Sandha is his last name. So he has created sort of around Mininet and all the set of tools and all gets created. So that baseline exists, and there is prior work in this space. There's some prior work which has also been done in context of partitioning computation among computers in a data center. So companies like Google and all worry about, like, when they are creating neural networks and the training and all, how do they distribute it among servers in a data center? Again, the problem at some level has a similar flavor to it. You're partitioning it across computers on a network. Our setting is kind of different. It's more about this edge cloud kind of setting. So your goal here would be that using a whole bunch of software already available, there are devices like Raspberry Pi, there are neural accelerators which just speed things up on the Raspberry Pi, phones, we have some others, Google's tensor processing unit, and there's a couple of others. So you kind of create something which is, again, can adapt to device and can adapt to changing network conditions. And you can start out with one or the other. I mean, maybe start with device, something which can just automatically tune itself to whichever device I'm running on, and then kind of look at the changing network situation. Okay, any questions? Okay, next one. So the idea, so I already mentioned to you that how we make use of this network emulator, Mininet, and there's another one called eMain, which has a similar flavor. We kind of fake a network. But when you are doing these designs of these kind of IoT systems and things like that, network is just one component. You also want to be able to fake other things. So one of the things you want to be able to fake is these IoT devices interacting with the physical world. Okay, because it's very hard to if you're developing something, and you want to test it out, it's very hard to kind of test out in multiple different physical scenarios because you have to physically go there and do stuff and all. So one thing which has happened is that people began to make use of games. So Unity and Unreal Engine, I guess at least those of you who play video games are perhaps familiar with it. They mimic the physics of the world very well, so as to give you a realistic experience of playing a game where you are kind of in the right physics and all. So what people have done is they have created simulators where you can have drones and cars and people and stuff like that in this virtual world. So there's one, for example, AirSim, for example. There's one which is out of Microsoft. There's another one called Car LA Sim. Okay, it basically mimics cars and all. Okay, and then Gazebo is kind of a totally open source thing. And kind of the idea is that these platforms are being used to train machine learning algorithms as well as to validate them. So, for example, how many of you have heard of things like AlphaGo and all? Some of you. Okay. So they use a method called reinforcement learning to essentially learn what policy the program would follow to win the games. And the way to do it is they play lots of games in parallel to kind of train that, right? So it's just a game. You can fake games. If you're a Google, you have access to thousands of machines, and you can just run these things in parallel and train the model which underlies that agent. But now imagine you're trying to train something for a car or a drone. What do you do? First, so you can do one of two ways. One is you can say, it's very hard to mimic the physics of the car and the around physical world and all. So, hey, why don't I go around and do it out in the real? Well, it poses a few challenges. Firstly, it becomes super expensive. I mean, even if you're a Google kind of doing this and at that scale, and particularly doing bad things, like if you wanted to learn about accidents, you're not going to have real world accidents because of the damage and all it will cause. So what people really do is then fall back to these kind of simulators and emulators. So now you have these agents, AI agents, which are supposed to control a real physical device being trained in a simulated world. And that opens up its own can of worms. But fortunately, the physics of some of these things is pretty good, but not perfect. So one of the challenges that a lot of people are worrying about is that after I have trained in this virtual world, when I move it to the real world, how well do things happen and all. But leaving that aside, the goal of this project is that we want to introduce new virtual sensors into this platform. So AirSim, for example, has drones. And on those drones, they have virtual cameras. So you literally can fly a drone inside AirSim. You can control it from a software outside AirSim. Using a TCP/IP socket, you kind of send commands and stuff like that. So to you, it actually would appear as if you're talking to a real drone. Except on this virtual drone, they also have a virtual camera. And this drone is flying in this virtual city or virtual landscape. And you are going to, and you're getting this video stream akin to what you would have gotten from a camera on a real drone flying in the real world. So people and then you can feed this thing to neural network to do things like object detection, stuff like that. AirSim also has cars, again with cameras, and I think they have a static notion of camera also. Someone has also introduced a LiDAR also. So kind of the idea out here is we want to add to these some additional kind of sensors. Okay, sensors like a thermal imager, for example, or some sort of a motion detector and all. So the idea is kind of learn about what does it mean to have the right sensor physics and all in this virtual world and kind of mimic it. Another cool version of this thing could be that could I take data from outside and introduce it into this virtual world. So there's a term which is floated around nowadays called mixed reality, and another concept called digital twin. And kind of the idea is that think of what is happening out here is as your model of what is going on. Okay, so there are virtual things and there are real things out there which you reflect inside this virtual world. And then you as a user can either go into this virtual world, put on virtual reality glasses and see what is happening, or I can be out in the real world. The real things are obviously in the real world. What about the virtual things? How can I take the virtual things and make them appear in the real world? Augmented reality, right? So I can have an augmented reality which overlays things. So I'm going to see this virtual world and there'll be a drone flying out here, which is really the reflection of the virtual drone out here. So there are a set of project ideas one can explore around this, but one which we are proposing is adding or exploring some additional, like a sound sensor, for example. There's nothing like that out here. That would be cool to have. So our drone is flying and it's sound and picking it up correctly depending upon the sensor location. What you'll get to learn about is really, I mean, how do these simulators work and stuff like that. They're pretty cool. So it's a cool technology to play with. Okay. So we have Sandeep again and Louis who lectured last week. Let me do the following. Since I'm at the midway point of the time, I'm going to stop on this one at this point and describe the remaining on as needed basis. So I would like you to read them and then just send me questions or ask questions on Piazza. I don't want to eat up too much time into my lecture time, but at least hopefully the first 10 have given you a flavor, but just to quickly flip through these things, the idea out here is to expose sensors and actuators as services. So one problem with sensors and actuators tend to be is that they're very hard to share among multiple things, and oftentimes their abstraction is very low. So when you replace a sensor by a same type of sensor modality but kind of a different version, then suddenly it looks very different. So the goal out here is that could we get IoT devices to expose their sensing and actuation capabilities as a service which applications can harness. Okay, so kind of raise the abstraction which goes on. So Louis would be a good person to talk to. This project we are actually doing is a pretty cool one. It's kind of motivated by a neuroscience group that we are working with. So what these guys are trying to do is they are trying to figure out how long-term memory formation works and how to help people who lose the ability to form long-term memory. So deep inside our brain, the theory goes that what goes on is that as our senses observe what is happening, then at some point, and remember, brain's memory capacity is finite, right? So what the brain continually does is analyzes, is this useful or is it useless? If it's useless, you go to sleep. If it's useful, then you want to remember it. So it's almost like there's a movie and the brain is a director and it's kind of identifying interesting segments, and then it takes those interesting segments, processes them, and puts them into the long-term memory. And later on, when you are trying to remember things, and hopefully if they were important things, then you will go and do a search by the index into that database switches. So the part of the brain which does this thing is something called thalamus. And if it gets bad, either for genetic reasons or because of some trauma, then at that point, the long-term memory formation gets bad. So what this group out here at UCLA is trying to do is trying to understand these processes and also design a prosthetic. The idea would be that now, instead of putting all the logic inside the brain and all, perhaps we can make use of these outside sensors that we can easily put. So imagine if we equip people with sensors and we continually monitor interesting things which are happening, right? I mean, for example, we encounter a birthday party, must be some important, so you kind of make a note of that segment, okay? And then the idea is to help brain form the memory. You stimulate that part of the brain. So there's a set of patients who already have some electrodes implanted inside the brain, which can essentially generate some signal to kind of supposedly help in that formation. The goal of the project out here really is to create this sensor suite which can detect interesting events. And interesting, no one quite knows what they fully are, but the hypothesis is these are things like when we walk into a new space, when a special event is happening, when you hear laughter or crying or some different kind of music. There are transitions that go on in our life which might indicate these things. So that's the idea out here. So again, you can read more. Yeah. Okay. The sensors and all are all there. So the focus here is really on creating this system around it to do this. Yeah, you can read up on these. This is the augmented reality stuff, but the goal here is visualization. So the idea here is that for many applications, it would be good, it would be cool if the hidden state inside the compute system were to be somehow visible in the real world. Like, for example, if there are IoT devices out here, but one of them is turning very hot, and if I have HoloLens or some other augmented reality device, it actually shows a red color overlaid on it. Or if it turns out some particular device is getting bombarded with a lot of traffic. So when I'm looking at it, maybe from the access point, there are some sort of arrows going overlaid, which is kind of showing the amount of traffic. So I can easily visualize what is happening overlaid on the physical world. So that's kind of the goal out here. Take the software state and reflect it out into the physical world to do some useful stuff or look at signals and stuff like that. Okay. Yeah, I'm going to skip the rest, and I'm going to add some more. You can read these and again reach out. So let's do a 2-minute break just to get over this long monotonous thing, and then we're going to start the lecture.
If we're interested in some of these projects, do we contact the mentor directly, or do we contact you?
Best, I mean, you can either contact me and I'll just introduce the mentor, or you can just directly contact them.
Okay.
Either way is fine.
And can we go just to the embedded lab?
You can go to the lab. The only thing is that they may not be there. Some of
Okay.
these, right? I mean, so it might be good to just find out a time that everyone
Okay.
is. Okay.
To send an email.
Send an email.
Okay.
Yeah. Send an email. CC me.
Okay.
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 Yeah.
Thank you.
And if you have trouble finding the email address, then
Okay.
just but
It's weird. Topic is about humans' brain
yeah.
activities,
So,
right?
so no. The topic is about outside world.
Oh,
We are providing you the context. So we are not messing inside the brain.
but it's sensing.
Eventually, the goal would be so. The sensing is all from outward-facing sensor.
Oh.
So the idea is that you are trying to find interesting things which are happening, so that we can trigger the brain.
Okay. But the way we trigger is.
Oh, there is already, these people already have a device inside their brain,
Okay.
and we have an external device which can communicate with that, and we communicate with this external device. Now, you are not going to actually work with the real humans, okay?
I
The
see.
focus here would be that, think of it like the following. Imagine that if I just had a camera, I was GoPro and I was walking around, all you do is you are capturing the image,
Yeah.
right? What we are trying to do is also detect interesting episodes, okay? And we are defining interesting episodes as change of location, like I'm walking into a room, or events like birthday parties and okay, right? These kind of key events. So, like if you look at that video sequence, for example, or sensor sequence, much of it is useless, less interesting. That's why we're trying to identify the interesting clips automatically. Okay.
That's pretty.
Yeah.
That can,
It's like
operate with something.
yeah.
Can
Then it
deceive.
can cooperate. Yeah.
Thank you so much.
Sure. Do you want to talk?
Actually, I'm not sure if I'm not actually talking about this project for schools right now, and I'm not even sure how to do this code. It's some project that I've been thinking ever since my undergraduate. Would you open to discussing it with me probably next month about this project, and if it works,
Sure. Although I must also say, I'm not. There are way too many students I have committed to, so I'll probably not be taking it.
I mean, if nothing else, I could probably get maybe some kind of guidance on how I could go through it.
Sure, I would be happy to. I mean, I generally, any MS students I take for firstly, I don't give DSRs, okay? And even it's usually after I've been exposed to them through looking at the performance in the course and also, it's very rare that I take someone who's not. But besides that, my lab is space-wise kind of quite full, so yeah, generally not. Yeah. Okay, sure. Okay, let's restart. So, this is back to where I left off last time around. So, we had begun to talk about I/O, how different ways I/Os happen, and I talked about digital I/O, I talked about analog I/O, and I'd given I talked about that how. Sorry. Yeah. In case of digital I/O, it's basically the ability to either read the digital status of the pen or control it. In case of analog, it's really A to D converter or D to A converter, and often, typically, you do need external circuitry and all around it. Oftentimes, these things come with additional peripheral support behind it, and one. So you would, if you look at these devices, you would basically see that there is a whole bunch of other stuff that is sitting out there. But this is just showing you kind of what the analog stuff is. Now, A to D converters, D to A converters tend to be pretty expensive. So there are other ways you can convey analog information outside. So an advantage of analog values is that you need a single pin, right? I mean, if you're trying to convey some value which can take more than, or it's not simply 0, 1, but kind of a range of values. The nice thing about analog is that if I need to convey 0 to 255 in steps of 1, I can just do it in a single pin with the appropriate voltage levels. And if I were to do it digitally, then I would need 8 bits. But you could also do this thing digitally if you are willing to somehow squeeze everything into a single bit. Now, one way of doing it would be to send through some sort of a bit sequential representation, right? Send the different bits one after each other, right? So the 8 bits go by one, and there's some sort of a decoder on the other side. But there's another cool way, and which is often used, and that's called pulse width modulation. And the idea is that the levels are my standard digital voltages, right? So they're corresponding to 1 and 0 respectively. But I generate a square waveform whose duty cycle corresponds to the analog value that I'm working with. And the nice thing is that something like this, I can very easily feed to analog circuits and get the right analog value. So for example, if I take these kind of signals, and if you think about if I feed them into a low pass filter, which only extracts the DC value, then the DC value here is going to be half the voltage, DC value here would be 3/4 the voltage, and so on and so forth, right? So I can basically discard the high frequency component. So the nice thing out here is I have a poor man's analog output. I say poor man's because I can get the value only by looking at long-term time intervals, right? It's not an instantaneous value. But I can do this twiddling of the bits much more rapidly relative to the dynamics of the underlying analog system. Like for example, if I'm trying to control a motor or something, the motor dynamics and all are at whatever kilohertz rates, right? And here I have a processor capable of operating at tens of megahertz, right? So I can certainly do this, can have an underlying frequency which is quite high and kind of fake the analog signal. So this happens a lot, both for input and output. So you can imagine I could send signals to an analog system via this means and only make use of GPIO, no D2A converter needed. And the reverse direction, they can send me signals like sensor readings and all, and I can use timers to measure the duty cycle and then get the value of the sensor, okay? In which case, no A to D converter needed. So, so you find support for this quite a bit, and indeed, if any of you have ever played with RC cars or drones and all, the motors there come with something called electronic speed controllers. And the output and those ESCs interact with the microcontroller using these kind of things, because the idea is you don't want a whole bunch of wires running, and you want to also avoid those A to D, D2A converters. So this gives a very cheap way of pulling things off. So anyway, so that's the idea. So motor speed control, motor position control, a lot of these things that you will find out there, servo motors and all, they interact with the MCUs using PWM signals, even though they're analog values in the sense that you are trying to represent something which has a continuous, whatever, changes continuously over a band of values, but you don't want to use analog signals literally, okay, that is varying voltage, but rather instead of varying voltage, you have varying timing, okay? And just like we have pulse width modulation, there are other versions of it called pulse position modulation. So that's another one where within a time period where the pulse occurs. So the pulse will always be fixed width, but its position will depend upon the value you are trying to convey. The negative of these schemes obviously is that the time duration over which you are working with is much lower than this, right? I mean, to convey the fact that this is 25%, you have to look at a long enough time interval, right? Because if I look at a short time interval, yeah, obviously here it is 0 and here it is 1. So that doesn't tell us much. You have to sort of low pass filter and then look at it. So for example, in case of motor speed control, what happens is that motors are surrounded by what is called an H bridge. And essentially what it is the set of 4 switches, okay? And at any given time, I would either keep all of them open, so no energy is provided to the motor, or I will have the opposite thing. So if I want the motor to move in a let's say in one particular direction, clockwise, let's say, at a particular speed, then I'm going to open close this pair of switches, left, top, left, bottom, right, to supply the current. And if I want the motor to move with a certain speed in the reverse direction, I'll take the other pair of switches. So essentially, and by very rapidly moving these switches through these waveforms, and the fact that, so where is my low pass filter now? I'm not showing any low pass filter, whereas I just told you that, hey, we need to low pass filter it. So what is filtering away the high frequencies? No, not the switching. The mass of the motor, right? I mean, it's the motor is a dynamical system, right? So the motor itself is acting like a as a low pass filter. So I don't really need to put anything. I just rapidly open close this pair of switches, and depending upon what the frequency is, that will affect what the switching frequency is. That's what will happen out there. Same concept gets used in power supplies for your laptops and all. They're called switching mode power supplies. Same thing is happening out there, right? The purpose there is different. You want to supply, even in the face of voltage variations, you want to supply a solid fixed DC voltage to your laptop or to your electronic device. So again, basically what happens is that it would have some structure like this, and this rate that you do is you control it based upon the voltage that you are actually observing at the input to the electronic device. So if that voltage starts drifting up, you slow down the, you lower the pulse width, lower the duty cycle. And if the voltage is dropping, you increase it. So you basically create a control system around it. Same thing with motor, right? If the motor starts slowing down and we measure it using some sort of a speed sensor, then I'm going to adapt this thing. So you create a control system like that. So that's PWM. It's pretty powerful, and it's so widely used that you would almost always find a PWM hardware unit on the processors themselves. Okay, it's basically nothing but specialized timer circuitry. Okay, you can design these things yourself in software if you want it, but then it's a lot of interrupt overhead and all, because every edge you are going to face an interrupt. So they basically shove it into dedicated hardware circuitry to manage PWM for you. Again, depending upon your OS that you are using and all, it may or may not be provided to you as is, but you can, if you attempt to fake it by twiddling the pins yourself, then the problem that often happens is that the accuracy with which you are able to do these things is not very good. Okay, there are two problems that happen. Firstly, you may not be able to get exactly 25% because a little bit of delay in handling the interrupts and all can cause issues. And the other thing is your timing may not be exact. For this thing to work nicely, you really need to make sure that you are the frequency at which you are doing these things are also very stable. If the frequency has a lot of jitter, then you will see effectively kind of they will creep into the system you're trying to control, like the motor, and you'll see vibrations or some other weird dynamics. So leaving it to the hardware as opposed to attempting to do it in software is very important. So software basically commands the PWM hardware to generate PWM with a particular duty cycle, as opposed to directly controlling the pins in software by wait for an interrupt, set a timer and all. And same thing in the reverse direction. When it comes to sensing, there are dedicated hardware units which take in a PWM signal and simply tell you what was the duty cycle ratio, as opposed to you attempting to measure them in software. So it's an example of something which is almost like an informal standard of sorts, like all these motors you buy for, like, if you build your own drone and all, you'll very rapidly realize what goes on. Let's see. Beyond these, yeah, go ahead, please.
So what are the cases that you would rather use ABC instead of?
Oh, okay, sure, good question. Firstly, when the bandwidth that you need is much higher. Okay, because these things, remember, for the PWM to do its job correctly, the dynamics of the underlying analog signal should correspond to many of these cycles. So let's say I'm doing this thing at 10 kilohertz. That means I'll probably be able to handle analog value changes which are in a 1 kilohertz range. great for a motor, but not great for applications where values are changing a lot more rapidly or need to be controlled a lot more rapidly. So it really boils down to what kind of physical system you are dealing with. If it is a rapidly changing phenomenon, then you better go back to, you don't have much of a choice but to go to A to D. The other part obviously is that the analog side needs to be able to understand these signals also, right? Not all of them are designed that way. I mean, motors happen, it's very common in motors, but a lot of other things may just want an analog value. The final thing is the precision, the bit resolution, okay? So if you think about it out here, for me to be able to control this value with a certain bit precision. So let's say I want to represent values 0 to 100%, and let's say I want to be able to do it in steps of 1 over 256, then I need 8 bits, right? So I need a timer controlling these things to 8-bit resolution, right? So now let's imagine I want to do it with 12 bits. Well, 2 to the power 12 is a much larger number. So it begins to have implications on the speed with which you can pull it off also. So I think at some stage you will realize that if I need a very fine resolution, again, I'm better off just going to the analog side. Okay. So high quality, you'll probably use A to D, D to A. If you can get away with lower bandwidth and all, then you can stick with PWM. So motors and speed sensors and those kind of things are the most common use case for this stuff. Yeah. Okay. So yeah, so beyond GPIO and AIO, there are a whole bunch of other examples of IO interfaces that you'll find in these devices. I2C, SPI, UART, USB, and a whole bunch of others. Okay, and the new ones keep coming. So there's serial, and then there are parallel ones like PCI. Okay, PCI Express or compact PCI, these kind of things. Some of the issues that sort of one basically faces is firstly, or broad dimensions in which they differ. What kind of data rate and over what distance you are trying to interface over. Okay, that's kind of the highest, most important thing. Serial versus parallel. Wired versus wireless. I don't know why I repeated them. Point to point or point to multi-point. Am I just doing A to B, or is it A to a whole bunch of things? Am I broadcasting it? Let me ask you a question. Serial versus parallel. If you want to do really high-speed I/O, which one would you use? How many say serial? How many say parallel? Okay, I heard both. Okay, so those who are advocating for parallel, what's the reason? Someone? High speed? Okay, so no one goes for parallel. Okay, so you're saying serial. Why serial? That is correct. And the fact that it is correct, you would basically see that all our high-speed IOs are actually serial, right? I mean, okay, so why is it that, I mean, defies intuition a little bit, right? I mean, one wire versus many wires. Why is the single wire one faster?
Well, I think in parallel, there's some point in speed where you can synchronize all the lines. So you need to do all the...
Yeah, exactly. So for parallel to work, all the bits across the wire, all the wires have to be in synchrony. And that is not easy to do, because as these wires move and all, but as speeds get higher, then even a tiny variation in their length, even the wire bend being different in one wire versus another, can cause dramatic changes. So getting parallel to work correctly at high speed is very painful because of this inter-wire synchronization that is needed. Serial by design eliminates that. Okay, so yeah, just something to bear in mind. So parallel interfaces exist. Besides the fact that they need too many pins for the reason that I described, they are not used. The advantage of parallel is that they are super simple to implement, right? I mean, I really don't need much of a logic on either side. Whereas with serial, I need all this serializer, deserializer kind of stuff going on both sides. But basically, long ago, we reached a point that was basically worth it. Okay, so while PCs until maybe 10, 12 years ago still had parallel ports. I don't think you can even buy a PC now which has a parallel port. Okay, I mean, they're basically dead. Okay, so yeah, too much animation here. I don't think there's anything new that I'm saying out here, so I can skip this. Okay, so the most common serial one which has been around is UARTs. It's basically a way for devices to communicate using essentially 3 wires. There's a ground, or we can say ground is shared, so there's really 2 wires, receive and transmit. And it's called UART. So U stands for universal. So I guess simply because it's very popularly used. A stands for asynchronous. So what does asynchronous mean out here? So the key challenge out here is that when I'm communicating like this between 2 devices, they have their own clocks, right? So somehow, if I'm generating these sequential, if one party is generating the bits and the other party is going to sample it, we need to make sure that the clocks are in synchrony also now, because otherwise, if there is a slight shift in the frequency, then after a while you will be sampling the wrong bit. Your goal is that, let's say that you want to be able to sample in the middle of the bit, let's say, simpler, in some simple terms, right? So you want to make sure that as the receiver is sampling it, it's always sampling at the middle of the bit. So the way these schemes work is that I don't, like different entities which may be sending me the data, they may have slightly different frequencies. So what we do is, at the initial thing, we send a couple of bits to learn the frequency. And so we send a particular pattern which will let us measure what the sender's frequency notion of a bit width is. And then I'll adapt my clock to it to sample it. So hopefully in your digital logic courses, you might have seen some examples of this, but the basic idea is this. Now, there are also synchronous serial buses also, where one party will send the clock, okay, so that the sampling could be done on the other side based upon the clock I am providing. That can only work with wired interfaces. If you are working over a radio, then of course I don't really have a way of sending that clock signal in, or do I? Can I send, can I have the 2 parties have the same clock frequency without actually sending a clock over? What are the different ways you could do it? So again, 2 things are talking over a radio, bits going out. I obviously can't run a clock wire to the other side. So what could you do?
Can you send it like an acknowledgement signal based on that?
Too late, right? I mean, for it to decode even the acknowledgement signal, the clock frequencies have to be aligned, right? Otherwise you can't sample. Yeah.
You have an agreed upon rate, like the baud rate that you want.
No. So we always do have an agreed upon baud rate. The issue is, I may think I'm sending at a kilobits per second, but because of slight differences in our clocks, for you it is actually 0.999, let's say. So that will cause an error to creep in. So how can we make sure that what I think of as 1 kilobaud is also 1 kilobaud for you, right? That's our challenge. Okay, we'll talk about in one of the later lectures, but there are some ways around it. You can use some very precise clock, right, and synchronize it once. Okay, so this is what atomic clocks do. So in fact, there are these things called chip scale atomic clocks, which are extremely good, as kind of the name might suggest to you. The only problem is they cost like $1,000 or so. So they're tiny chips, but then suddenly you're looking at a very different category of devices. Another thing which gives you good timing and which you can then use to is GPS. GPS we think of as positioning satellite, but it's actually positioning and timing. It also gives you very precise timing, so you could use that also. So there are ways around it, but none of them apply to a processor talking to a neighboring sensor. Okay, you're not going to be using those. So usually then you basically make use of some initial bits to then train the network. So this is so common that almost every MCU is going to have that. You also see this term RS-232 quite a bit, and some other terms like RS-245 and all. They're basically UART with some different voltages. So when we normally refer to UART, we basically say the voltage values are whatever voltage values the MCU might be using, like let's say a 3-volt MCU. Whereas RS-232 is a very specific thing. It's like 12 volts and stuff like that. So it's very specific voltage. So what you need is some additional analog circuitry to shift the voltages. So normally when you have a device which needs to talk to something which is in a chassis and all, it's probably going to be an RS-232 port, and therefore you need that. On the other hand, if you have these embedded boards and all and you want to have them talk to your laptop, there are dongles you can buy which basically work at the level of the standard UART voltages, 3 voltage and all. So but one has to be careful. If you plug in RS-232 voltage to this thing, you may fry some stuff. Okay, let's see. Yeah, so when you send a set of bits over the serial line, then typically you send a start bit, which is what helps the timing be right. Then you send the data bits, and then you send some additional parity bits and stop bits. Okay, so you need to make sure that both sides are speaking the same thing. So for example, 8 data bits, no parity, and 1 stop bit would be called 8 and 1. Or 7 data bits, even parity, 1 stop, and so on and so forth. So you'll see these kind of jargons, and this is similar to if you have ever attempted to interface something to your computer. You have to set the serial port settings to be correct. So you have to set the baud rate for sure, but you also have to set these other things like was there a parity bit, was there a stop bit, and so on and so forth. So very important to be able to do that correctly. So essentially this kind of shows a letter W going out, the line was idling, there's a start bit which was sent, and then after that rest of the stuff goes out. Okay. Yeah, okay. I'm going to skip all of that. The other very common bus which you'll encounter is I2C bus, Inter-Integrated Circuit Bus, developed by company called Philips from Europe, and this one is a synchronous bus. Okay, so here it is what is called as multi-master, as in I can have multiple entities on that bus, and anyone can transmit and anyone can receive. They have some sort of an address which helps you do that, and again 2 lines only, except that one of them is the clock line. These lines are pulled high by default. So essentially what happens is on the wire there is a resistor which pulls the voltage of the resistor to be high, and then all the other chips which are sitting on it, they do not drive any voltage. Okay, so essentially I think all but one of you are electrical engineers, so hopefully this is not too much of an imposition, but kind of the idea is that the wire is pulled up and connected to a high voltage, and then the other entities which are sitting on it, they don't drive it at all. No, it's almost as if they're not connected at all. And then whenever they want to drive it, one of them is going to be the master who's actually putting the data out. Then they choose to drive it, and then it can pull it down to 0 or leave it at 1. Others are still kind of disconnected literally. So this is referred to as open collector type circuits or other similar names given to it, but they all have this common thing that I can almost as if electrically I'm disconnected from the wire. Okay, so there are multiple entities, and at any given point in time, one of them, the one who is transmitting, is the one who's going to be sending things out. So I2C is used quite a bit nowadays because it can go to higher rates. Partly because it can go to higher rates is because it is synchronous. And so there are versions of it which can go to a few megabit per second, and it is also nice in the sense, unlike UART, which is point to point, this is multiple entities. So you can have at different times different entities transmitting and talking, and you will need and it provides some address. So it turns out that there is 7 to 10 bits of address which manufacturers provide, and then at the I2C level, you can say, I want to send this byte to this device with this address. And there are a bunch of other stuff exist, and there are kind of few different speeds available. So I2C, very, very commonly used. Third one, which is probably the simplest of the thing that you can imagine, which is again very widely used, is something called SPI, serial peripheral interface. Again, you will find it quite a bit, and the way it kind of works is that it has 4 signals, okay, and one of them is a clock signal. So one party supplies the clock. You have data lines in the 2 direction, and then you have a select line. So essentially the idea is that this master, which could be CPU, it basically selects one of the slaves. So imagine there could be many such devices attached to the CPU, and each one of them will receive the same of these 3 pins, but this SS bar, the slave select pin, would be different for different ones. And so you select a slave and you push the data to it, or receive the data from it. So this is very simple, because what happens is once you select the slave, then essentially on every clock tick a data bit is sent out. Very easy to implement, because essentially in software or hardware you can say next clock tick, next data bit, next clock tick, next data bit. No start bit, no end bit, nothing. It's literally as if you're talking within your own circuit, within your own chip, the way you would have talked. So super simple to implement, and therefore very widely used, and you can even do it in software if you can keep up with the clock rate. Okay, so with some carefully scripted software design, you can kind of pull it off also. So you'll find SPI is used quite often to talk to EEPROM, flash memories, these kind of things, and all radios, things like that. So super simple, but then it places a lot more burden on the CPU. So I2C usually is supported by some hardware entity, whereas with SPI often you are on your own. Okay, and you can support multiple slaves by just having multiple slave select lines. Okay, so very simple to do. Okay, I'm going to skip these slides, 1 or 2 slides again, and there are some others also. I've covered the 3 most common ones that you are going to encounter. UART, very commonly used to talk to your computers. I2C, very commonly used to talk CPU to multiple sensors, making a chain, and SPI, kind of the super simple, super dumb one. So no right or wrong answer. It's just that good to know that they all exist, and usually the 3 that I have described, they're common enough that any decent RTOS or embedded OS is going to support all of them. I2C actually is also used heavily within the PC architecture also. So it turns out like when you things that talk to your fan or LEDs and all, they are all done using I2C. If you have ever assembled a PC yourself, then those wires which go from the motherboard to the fans, they're all I2C buses. Okay, let's see. I think I can skip these. Yeah. Another type of, I'm not going to detail some of this thing out here, but another type of port or that you will encounter quite a bit are for debugging and programming. So it's not, the purpose here is different. The purpose here is not for a CPU to talk to a serial device and all, but rather for you to be able to program the device and for you to be able to monitor the state of the device. Okay, so debugging, programming and debugging. Programming is important because remember I told you the program is on that flash memory inside the chip. How do I program to this thing? And debugging is that I don't have the luxury of whatever a printf and stuff like that. How can I examine deeply the state of the chip? What is the value in a register and all? We don't have GDB or some other debugger running and all. So how do we kind of make these things happen? So usually these chips come with some sort of port for us to be able to do that. There is an industry standard port called JTAG, Joint Test something. JTAG is kind of the common name. So you would often see like JTAG programmers and stuff like that and all, and the chips have JTAG ports, and then they are connected to each other so that your overall system would have a JTAG board, and there would be some sort of a dongle to program this thing. So a lot of embedded systems basically then have this JTAG port through which you can program. So you can download stuff to the memory on the board, and you can debug the CPU. So you can say, stop the CPU, tell me the value of the register, move forward one more clock tick. You can do all those types of things. The problem with that kind of approach is you need the special JTAG hardware. Now, they're not terribly expensive, but can be kind of painful and all. So what people have more recently begun to do is they build all this logic to program the chip and help you debug the chip and all on the board, and then have the whole thing being exposed to you via USB. So that you can just take your system and plug it into your computer, and then it makes use of standard USB profiles and drivers to basically make things work nicely. So embed operating system, which I'm going to talk about in a bit, is an example of that. And to be able to make that happen, ARM kind of defined a set of interfaces around it. So there's something called core side debug access port, which exists in all ARM control processors. And then they defined a way to access that port, that DAP port, in a standard manner over the USB. And so basically any chip, this basically means any ARM processor, any board designed around the ARM Cortex microcontrollers, basically has a good way of talking to our laptops. And the reason it works is they made another trick, that they made that interface follow what is called as the USB HID connection. HID stands for Human Interface something, okay? Human Interaction Devices, sorry, HID, Human Interaction Devices. So this is the USB profile which is used by keyboards and mouse and stuff like that. And the philosophy was that almost any computer worth anything will have support for keyboard and mouse kind of devices and all. So basically HID drivers are built in pretty much universally. So anything which supports using this basically is good to go. You don't need any special drivers and all the way you would for those JTAG dongles and stuff like that. So this has now caught on, and it's super cool because basically without any drivers and all, you can basically very easily interact with these things. So now what happens is a lot of these devices come with support for this and UART, and there are UART to USB communicators. So basically your devices appear as this so that you can program and debug them, plus the UART so that you can communicate with them. And there's a third very common USB interface that exists, that's called the SD card interface, right? Flash memory. So usually you will also see some of these devices, they appear as flash memory. So when you connect to them over the USB, some of their memory will be mapped, will appear to you as a flash memory. Okay, so a lot of these devices then basically make use of basically the universally supported flash memory interface, so that you can download files to them very easily, just drag and drop. UART, because you can hook up your terminal to it and then exchange bytes and all to the software running on the device. And then finally this full CM sysdap, which is how you can program them and interact, do the low-level functionality with them. So so this is standard and very useful. But the other one, like I said, is this JTAG thing. And for more, let's say, I would say more powerful or less user-friendly systems, JTAG is kind of lets you do a lot of things. Another bus which is very common in embedded world is something called CAN bus. And this is used very heavily in automotive industry in particular. It stands for Control Area Network. And so in your car, there are these little computers called ECUs. Okay, engine control units is, I think, what they stand for. And there are probably a few tens of them in any car nowadays, if not more. So there's essentially a distributed network, and then these things all talk. So like, for example, the brakes might be talking to some control unit through these things. Okay, so it's basically a bus which exists inside the car, and they all talk. This is a pretty old bus, but main thing is it allows for peer-to-peer communication over this network. Very slow, like a megabit per second kind of stuff, but it provides a priority-based communication capability. So the idea is that different devices which are sitting on this CAN bus have different priorities. And if two devices want to transmit at the same time, then there is a competition which takes place, and then the winner gets to transmit. So this is how you assign priorities, like maybe the braking system will get higher priority than your entertainment unit, for example. So the way CAN bus does this arbitration is kind of super simple. What it does is, again, the data lines themselves of this bus, these lines are again that voltage pull-up type lines. Okay, so the idea is that all the wires out here are just attached to a resistor and pulled up in voltage. And a device, when it wishes to transmit, only then it will pull the wire up or down. Otherwise, it just disconnects itself. Okay, electrically disconnected. And now what happens is, let's imagine that two devices simultaneously want to transmit. So the whole thing is, there's a clock. So there would be an instant where you are eligible to transmit, but it's possible that two devices simultaneously want, say, break one and my nav unit both want to transmit. So what happens is, they start sending out on the transmitter their priority bits. Okay, so the priority is let's say an 8-bit number. So they will send out the highest order bit and the next higher order bit all the way down to the lowest order bit. And simultaneously, they listen to the data line also. Now, what will happen is, if two devices are sending out the same bit, let's say, in our case, let's say two devices are conflicting.
Here's what I found.
Okay, I don't know why. So if they send out the same bit at the same time, then they will hear back the same thing. But let's say one sends out a 1 and the other sends out a 0. The wire is pulled up, so the wire will now be pulled down, right? Because it's a wire with a pull-up resistor, and the person who's transmitting 1 will just not doing anything to the wire, but the one who's transmitting a 0 is pulling it down. So now what will happen is that the person who transmitted a 1, it will see a 0 coming back, whereas the person who transmitted 0 will also see a 0 coming back. And the idea is that if you see a discrepancy between what you transmitted and what you are getting back, then you lost. So the winner always is the one who is overriding, right? So if so now imagine K parties, they all started out, and anytime whosoever has a discrepancy drops out, and everyone has a unique priority. So by the time we hit the end of all my 8 bits, only one winner would be left. So essentially, you conduct this 8 round in our case, because it was 8-bit competition, and then at the end, one party is left standing, and then it transmits its message. So there is this n round competition followed by the actual message transmission, and the whole process repeats in this process. So this kind of bitwise arbitration is how CAN bus does its job. And there are all sort of papers around, like what are the implications of this scheduling strategy and all, but basically it is highest priority one gets to transmit. Now you can see problems out here, right? Because always the highest priority one wins. So if the highest priority node has been somehow hacked or is just buggy, then it can starve everything else out. So you might want to have a different scheduling strategy, for example, to kind of make sure that other stuff goes on. Hacking into ECU software and all is not entirely unknown at this point, and there are all sort of devices and all that you can buy on eBay which messes with this thing. There is a little port at on the driver's side of the car, if you just go under and kind of it's like a has I think around 30-40 pins, and there are devices which are designed to plug into it. This is what your car mechanic do, or when you go for a smoke check, they kind of hook up to it. But you can buy these things for monitoring your driving habit and stuff like that, because a lot of very valuable information is transmitted over that port for you to read, like what was the fuel consumption, how fast the car was moving, all those kind of stuff and all. So people have developed things by hacking through that port and modifying the software on the ECUs as well. So anyway, that's CAN bus, which comes out on that port, and this is how it kind of works. So I'm going to stop out here. We're going to see you on Monday. I'm going to post additional project ideas, also a few of them, and if you want to pursue any of them, feel free to directly contact my students or write to me and I will connect you.